Welcome back. So, we have defined the Fourier transform of tempered distributions in the last class, and we also seen that the temporal distributions are is of that order, and that also indicates that these are all of finite order. Okay. So, also T is in zeta prime, that implies T is of okay. All right. So, we go to the next class, next section. So, now look at here zeta. Zeta contained in L1 that contained in zeta prime. So, on zeta L1 induces L1 and zeta prime. So, you have defined Fourier transform for L1 functions in one way. You also define now the Fourier transform using the distribution concept. So, both induces distribution Fourier transform on zeta. You see, one Fourier transform on zeta coming from L1 definition, other one, and basically if you have f in zeta, so you have to understand f is in zeta. So, how do I write here? So, you have f in zeta, so then you have f is in L1, and that gives you f hat, some f hat, okay, and you have the Fourier transform. So, f is in zeta, this is also in zeta prime. So, that gives you the Fourier transform. So, what do you mean by a Fourier transform? The Fourier transform given by the distribution. So, f is in zeta, you treat f is in zeta prime as Tf. So, its Fourier transform. So, this f hat now gives you Tf hat. So, basically, so the question is that you want both this Fourier transform to be the same. In other words, the question is that Tf hat, that means the Fourier transform given by an L1 function. Hence, we have to prove that Tf hat is equal to Tf hat. It is not difficult. So, let us take phi is in zeta, Tf hat acting at phi not that way. I will take the right side first. I will take Tf hat, can prove it both ways, but this is more convenient. This is by definition Tf acting at phi hat, and that is equal to integral of f phi hat. You see, it is in Rn. Now, but this is equal to f is in zeta, recall that, do not forget that. When f is in zeta, this is equal to f hat b. This is nothing but your weak Parseval relation. Parseval relation. So, this is nothing but, so it is just a application of weak Parseval relation. So, you have that. Okay. So, you also have this easy results which I will just state, and if t is in zeta prime, again just like zeta, you get the polynomial, you can multiply by a distribution by a polynomial, and d power alpha of t, this implies is in zeta prime. So, you have all that operations, and you also have your d power alpha of t hat is equal to, I will write down the same formulas. Okay. There may be a possible coefficient depending on your definition. Okay. And you will have d power alpha of t acting at hat is equal to psi power alpha t hat. Again there may be a possible coefficient. Okay. I do not want to, but you can write down all that details. So, just some trivial examples, and I will just mention a couple of difficult examples. I do not prove it here, probably I need more time. So, delta is in E prime, you see, with compact support, and therefore that implies delta hat is well defined now. You see, for your operations, important operators you can well define. Okay. So, what is delta hat? You can easily prove that delta hat is equal to 1. So, I will not do it. You just write delta hat acting at phi is nothing but delta acting at phi hat. Okay. And then you can see that is nothing but 1. Okay. And 2, what about 1? 1 is not in D. Okay. But yeah, 1 is only in C. Okay. 1 is in zeta prime, not even in D. 1 is not in zeta. Okay. Of course, 1 is in E. That is true because it is a continuous function, but it is not D or C. So, the Fourier transform of 1 cannot be defined in a standard way, but 1 as a zeta prime you can define, you see. So, whenever you are defining Fourier transform, carefully define on with respect to what thing you are defining that one. So, 1 hat you can prove to be delta, you see. And one more example, maybe I will compute here. So, 1 is not in zeta and 1 is also not in L1. Of course, 1 is not in L1. These are all functions. So, you do not have your not in any LP for that matter, but as a tempered distribution you can define and your 1 hat is in T. So, I will also do one more computation, simple computation, d delta by dxk. Again keep your definitions of Fourier transform properly. So, the coefficients accordingly you have to modify. So, what is this? That is the question. So, phi in zeta. So, because delta is a tempered distribution, all these d delta dxk are all tempered distributions. So, you can define the Fourier transform of all the things. So, d delta by dxk acting at phi, its Fourier transform acting at phi is equal to d delta by dxk acting at phi hat, and that is equal to minus delta acting at d phi hat by dxk. Do that one, and that is nothing but minus d phi hat by dxk at 0. So, you have that one. So, what is that one? So, there may be again some coefficient depending on your definition. So, I do not write that definition because I have used in my computation slightly different. So, that coefficient psi k phi, that you know, the Fourier transform of the relation at the 0, you have that one. So, that can be written as some coefficients approximately psi k phi, and at 0 it is a v of psi, you are evaluating at 0 of that thing d psi. So, it is basically at some psi k phi. Okay. I told you there will be a coefficient like I or something, if I remember correctly. So, you can do this coefficient, compute the proper coefficients according to your definition, compute the correct coefficients. Okay, do that one. So what is precisely telling that symbolically you can write d delta by dxk as expected. Its Fourier transform is nothing but that constant into psi k, means the action is this one should act it. So it's a precisely, if you differentiate, same rules, same things what you are working out. Coefficient, as I said, whatever definition you are using it, you write down what exactly. So you have to write down here correctly that coefficient. In one computation it will come I, for other computation there will be 2 power 2 pi power will be there. Okay. So another example, that is 4, is a bit hard example to work out. So I will refer, you can, if you want you can, because there is a multiple choice of values, how to choose values. So you can look this very nice book on distribution by Strickarts. Okay, distributions. It gives you, motivates you nicely, but it is given in view, the mainly say typically a harmonic analyst, so it's all written everything in more in a Fourier analysis point of view, the entire writing of that one. So the example is fx equal to e power is mod x square. Okay, x s not equal to 0 real. It's bit hard because to choose the correct values. That may require half an hour or 20 minutes to explain everything. So I will not do that here. So I will just write down the answer. Here I want to remark that one, this is not integrable. You have to be about not integrable. So you don't have the Fourier transform in that point of view, because his power I s mod x square is not an integrable function because its modulus is 1. But then this is a bounded continuous function, and that means that as a distribution is a tempered distribution. So you can compute your Fourier transform. So to justify what Fourier transform, even though it is a function, you are not able to define as an in the normal way you can't calculate it, but you can calculate this way. So just let me write down the answer. So it's an, I don't call it an exercise, or see the book. Okay, e power I s mod x, its hat, so it's an action on its hat, action on phi. That's what you want to write it. So this is of course nothing but e power I s mod x square over phi hat. Okay, which you can compute to be, again it depends on my pi by is, and is e power minus mod psi square by, there is an I here, I hope it's everything is correct, mod psi square by 4s. Okay, yeah, and there is a power also n by 2. And if I remember in this calculation I have used all these definitions are used this, that e power minus ix dot psi. But in the preliminaries you put a constant here. Okay, so according, if you are using that definition, these constants etc., there may be a minor change. And maybe one more example, and another example which again, so different situations I am giving. These examples given, it's a function, but it is not an L1 function, integrable function, but as a distribution you can compute it. Now another function f of x e power minus t, you have typically seen e power minus x square computations. So this may be slightly easier, but it is fine. This is rapidly decreasing, of course rapidly decreasing, but not differentiable at the origin. At the origin. Okay. Hence, this is strictly speaking is not in zeta. It is not as infinity. Oh, sorry, there is some. Okay. So this is not like minus mod x square, which you are already computed. So, so differentiable. So for n equal to 1, let me write down the answer. N equal to 1, you can actually compute this one. Again you have to do it as a tempered distribution. So you see f hat of psi is equal to t by pi into t square plus psi square. Okay. And for higher dimension also you can compute it and you can do that one. So with this thing, so it is nice to better to be comfortable with your Fourier transform, not only and work out few examples of Turnberg distributions and that Fourier transform. But with these lectures what is achieved is that you are able to define the concept of distributions, now certain class of distributions, in particular all LP functions. So if you take an L3 and other LP functions, you will not get as a function, but the derivative, the Fourier transform will be a tempered distribution. You can be used as a tempered distribution. Now next we go to, so I will begin with that. So starting with convolution. As mentioned in the introduction, Fourier transform and convolutions are two very powerful tools, and when they combine it is a very potent weapon, as in PDE in particular and also in many other analysis like signal processing and other kinds of things. So we need to introduce again the convolution. So we start with formally introducing 4 functions and then you treat functions as distributions and what formulas you can give. So it actually gives you very natural formula, and then we will begin with that one. So let us give in with a formal definition. When it is valid etc., we will slowly do it. So what is the formal definition? Since you are already used it, formal definition, if phi psi are 2 functions, validity we will check it, defined on Rn. So the convolution is a convolution product denoted by phi star of psi. So that is the denotation, defined as phi star of psi of x is equal to integral of phi of x minus y psi of y dy. Of course again it is in Rn, this is by the translation invariance of the, this may not be meaningful, okay. Let us not bother about the meaning, but once it is meaningful you can just use the translation invariance of the Lebesgue measure. This is also equal to phi of y psi of x minus y dy. So, that immediately implies the commutativity of your that is a very important property. Whenever you define the product, the checking its associative law, commutative law are all important. Okay. Associative law, commutative may not work for every operation, but associative law is important. So, in fact we use later to define a thing convolutions, the associativity. So, this is nothing but the psi star of E immediately by definition. So, it is just a translation invariance of the measure. So, the convolution products, that means convolution if x is commutative. A very nice property immediately. So, do not forget about the definition, whatever it is we will define it this way. Okay. So, we will start with a kind of, you are already seen one important application you have seen, convolution is used to approximate, convolution we will see that is used to approximate functions by smooth functions, So, in some sense, convolution is a smoothing operator. You will see that one, convolution is a smoothing operator. That means you can convolve a non irregular function smoothing operator. In fact, you can take you will see that one, even we will use convolution to approximate distributions by smooth functions. Okay. So, by convolving with very bad irregular functions or distributions by some smooth function, the convolution will become smooth operator. Okay. So, maybe one last property we will, maybe I will prove it to tomorrow, we will see. So, let us see when it is suppose if phi and psi are continuous in Rn, and one of them, that means they are all in C of Rn, okay, continuous functions in Rn, and one of them have compact support, then phi star of psi is well defined. Okay, phi star of psi is well defined, and that is immediate, because if you go back and see this one, if one of them have compact support, this integration is on a compact set, both integrations are on a compact set, and phi and psi are continuous, the product is a continuous function and you integral is finite, and phi star psi is okay. So, on the smooth case you already have that one. On the other hand, we want to establish and what sort of phi and psi, your phi star psi is well defined. Now, Another for LP function we wish to establish well definedness for LP functions. Okay. So, one trivial thing, if phi is in L1, if phi is in L1, one immediate thing L1 and xi is in L infinity or vice versa, that imply phi star psi is well defined and it is in L infinity, and you look at it phi star psi of x immediately is less than or equal to constant. What is that constant? Norm of psi at infinity. So, immediately you get it norm of phi at L1 into norm of psi at infinity, L infinity. You see, the other way also, if phi is psi is in L1 and phi is in L infinity, you get the reverse thing. Further, okay. Further, if they have compact supports, further support of this you can verify G also not f jar of G, we are using this notation. Phi star of psi is contained in support of phi plus support of psi. This I believe it is not a difficult thing, but still to make your convolution product comfortable, I will leave it as an exercise. Okay. One more theorem. Should I prove that one, or I will prove it tomorrow? Okay. Suppose phi xi eta. So, tomorrow I will give a quick proof. It is not very difficult proof, but you get comfortable that phi psi and eta such that you can take the convolutions phi star of psi, then you take convolve and phi star, assuming that the well definedness is there, are well defined, then they are equal. So, it is very crucial to do this. So, this is a proposition. Again, it is not very difficult to prove it, but for the comfort of it I will give you a quick proof of that. Okay. So, yeah, I think I will stop here and we will continue the lecture tomorrow. More on convolutions and all that, we will prove it in the next class. Okay. Thank you.